So I'm here to tell you a little bit about the IEEE Council on Electronic Design Automation, CEDA, as it's known, or Council on EDA, as we prefer. It was formed in 2005 by mostly people that were involved with a conference such as DAC. So we will be 20 years in 2025. So we're actually starting to prepare some celebratory events, including ones that will be here at DAC next year. So be on the lookout for that. So what is IEEE Council on EDA? It's a unit in IEEE, which is, as you know, the largest technical organization in the world. And it deals with theory, implementation, and use of EDA and CAD tools to implement not just circuits, but also systems. As we know now, the focus is really at the system level. This includes tools to automate all the aspects of design at all levels of abstraction. And the goal and the vision of IEEE Council on EDA is to be the leading provider of technical information and the community gathering for everyone working in this area. So that's really our goal, that's why we were formed. We were actually formed by several societies existing in IEEE, where there were people that were doing design automation with slightly different applications, but realized that there was a commonality of interests and there was really no home for them to get together, to join, to organize the conferences. So these are the funding societies: antennas, CAS, computer, electron devices, packaging, etc. All of these are founding member societies of the Council on EDA. What exactly does the Council do besides organizing nice lunches for people like you? We also organize conferences, we sponsor conferences. As you know, DAC is one of our flagship conferences, but we also organize, I think, over 100 conferences that we sponsor technically and financially sometimes. The flagship ones are Design Automation and Test in Europe, that Design Automation Conference where we are now, ICCAD, which happens typically in October, the Embedded Systems Week, and the ASP DAC. This is actually not in chronological order. Actually, chronological order, ASP DAC would be the first. It happens typically at the beginning of the year. Besides conferences, there are lots of other things that we do. But before I move on to that, I want to say that for conferences, there are a lot of opportunities that we can help you with. If you're thinking about organizing a conference, we can help you with the financing, we can help you with the organization, with the publicity, with the advertisement. We can also help you if you're not doing a conference or a full conference, but you're starting or want to start a workshop or a symposium. Please come talk to us and we'll be more than glad to help you out on that. We have chapters throughout the world, and we are looking for volunteers that want to start chapters in their part of the world. So as you can see from the map, there are a lot of regions still that we have volunteers. We know we have volunteers that live and work in those regions, and they don't have chapters. And probably they should, because we can provide them with resources and help them organize events in those regions that can be of interest to all the participants in CEDA in those regions. So again, come and talk to us if you are in a region that is not shown here as having a chapter. If it's shown as having a chapter, contact your chapter chair or talk to us and we'll let you know who he is. Like I said, conference is not the only thing we do. We also have publications where the research that you guys are doing, which you publish also at DAC and other conferences, then gets archived, typically in a more substantial manner, a more longer-term manner. So we have multiple publications. I'm not going to read them out for you all. I assume that you can all read. But I'm going to point out that we have a new publication that we are also co-sponsoring with the Circuits and Systems Society, which is the Transactions for Circuits and Systems for Artificial Intelligence, a topic that I'm sure some of you might have heard about. It has been talked about at DAC here and there. And it's a new transactions that is starting, so please take a look at it and send your best work there. We're very hopeful that this is going to become also a top IEEE journal and a top publication in IEEE. We also have and promote awards to recognize the people in our field that do excellent work, and I'm sure this includes a lot of you in here. So with the Electronic System Design Automation branch of SEMI, we sponsored the Phil Kaufman Award for Distinguished Contributions to EDA and the Hall of Fame, where we put some people that did not get the Kaufman Award, but were certainly deserving of it. The Richard Newton Technical Impact Award. These two you certainly heard today if you went to the keynote. You heard that there were mention of them and they were awarded to some people. Actually, Mircea is here. He was awarded today with the Richard Newton Technical Impact. And we have several Best Paper Awards from our publication. We have the COO Early Career Award for those of you that are starting in this field, and several distinguished and outstanding service recognition. We, of course, also promote, as again you saw today on the keynote, the elevation to IEEE Fellow, which is the highest grade of recognition that IEEE bestows on its members. We have a distinguished lectures program whose objective is to access to experts that promote the field and show the latest work in the field of EDA. There are multiple DL distinguished lecturers that are available for talks. They can go to you if you are a member of a chapter. We can organize visit by one of the distinguished lecturers for a local presentation, or these can be done also online if that's also possible. Please again get in touch with us if this is something that you want to see happen in your neck of the woods, to your students, to your colleagues, etc. We have a student travel grant program. So if you are here and you are a student, or if you are a professor and you have students, which you probably should be, we have grants for students traveling to CEDA organized conferences. Sometimes in the largest conference, these are managed and organized by the conference itself, but they're also open in general for any CEDA-sponsored conference. So students, please get in touch with us if you want to take advantage of this program. We have several education resources, including a presentation library where we archive, for instance, the Luncheon talks from all of our conferences, so they're all there. So the Andrew's presentation will later be also archived in there, so please check it out. What can the council do for you besides what I've said in conferences and publications, technical activities organized? We also have a lot of work in standards. We have people dedicated to working with the industry on standards. It's another area. And of course, networking, which is really the whole point of what we are here for. So how to get involved? Lots of opportunities, please. IEEE, CEDA, and IEEE in general lives off of the work of their volunteers. So please become a volunteer, offer some of your time to do activities, to organize activities that are interest to you and to all of your colleagues and all of your peers. That's really the lifeblood of IEEE and certainly the lifeblood of the Council on EDA. So check us out on social media, on the website. And if you have any doubts, please contact us. And I will be happy to provide you with more information if what's available on social media is not sufficient. And now that I think I've bored bogged you enough. We'll move on to the main event today. And the main event today, what is it? Let me check my notes. I'm not exactly sure I know what the main event is. Oh, yeah. It's the distinguished lecture lunchtime keynote. Lunchtime because you just had lunch, and keynote because Andrew will come here and talk. Andrew Kahng is, he needs no presentation, but what the heck, I'll do it anyway. He's a professor in UC San Diego. He was visiting scientist at Cadence for a few years and the founder and CTO at Blaze DFM. So not only is a professor and a researcher and a distinguished researcher at that, he's also an entrepreneur. But I think you knew that already. He co-authored books, journals, articles, very long list. He has, I believe, 35 patents. If I've missed one or two, it doesn't really matter. It's a long list. He is a fellow of IEEE and ACM, so he's been bestowed with the highest recognition in both organizations. And he has served, I mentioned conference here, and I think Andrew has served as general chair or as TPC chair or as a member of the program committee in all of them in multiple years, so I'm not going to list all of them. He was involved in the ITRS roadmap for a few years and led that effort. That's a very important effort for everyone in our field. And more recently, he was the founder and a strong person behind all the efforts in open access through the Open Road program. And I'll stop at that and move on to Andrew before he gets upset with me. So don't save. Let's get this out of the way and do.
This thing here, that's a pain. Thanks a lot. Hey, well, thank you very much for the kind introduction, and hello, everyone. Many thanks to Ian and others in CEDA for inviting this talk. My hope is to provide a bit of food for thought to accompany the good food from CEDA, and let's go. So I'll try to motivate a few takeaways, some with clear actions for us as a community. And these are just a few of many possible takeaways because this is my usual blurt of accumulated thoughts from 20 years. EDA holds the main levers for scaling. That's a takeaway. At the nexus of AI and EDA, academia must enable itself. And there's culture and coordinations to work on. AI and ML in EDA, it's difficult. Quality of optimization is hard. Gen AI, Deep RL need a lot of data, much more so than Bayesian methods or decision trees. We need targets to aim for, and so on. Innovation that has lasting impact demands shared and very patient effort and sustenance. And we will depend on proxies, PDK, enablement, designs, and tools. And there are gaps in the proxies that we have at hand today. And optimization has rich vistas that are yet to be pioneered, and openness will help us all race forward faster. Okay, so let me start with a framework of EDA and scaling. And I'm sorry if you've seen some of these slides or many of these slides before, but bear with me. Okay, we know what scaling is, at least we know the word. It means doing better with less resources, including people and time. And the value scaling that we have always known as Moore's law is very demanding. 1 week is 1%, or you go and have to play in a different game. And scaling is increasingly design-based. This is great news for everyone in the room. AMD's CTO 2 years ago in his DAC keynote pointed out that at the 3 nanometer node, design technology co-optimization, or DTCO, added more value than intrinsic scaling, and that the trend would only continue. And then this is a famous chart from Andreas Olofsson at ISPD 2018, showing the cost of designing silicon in leading nodes. And innovation was running into these barriers of cost, expertise, and risk. So architects and chip designers couldn't tell how good their ideas were. It was just too difficult to explore hardware realizations. And Andreas, of course, pointed a finger. And he backed this up by funding a program of open source EDA projects, including Align, FASOC, OpenRoad, and others. So design and EDA have this main burden of maintaining the value proposition of silicon in new nodes, which means that to scale and innovate in hardware design, we must also scale and innovate in EDA. If the future happens to bring us that long tail population of designers and designs, then in addition to EDA innovation, we must also have more bespoke EDA and the EDA engineers who produce those tools as well. So the scaling challenge is one of design, EDA, and people. Okay, so what about EDA itself? Very important. Sorry, I say this every chance I get. The heart of EDA and IC design is optimization. Do better, always. So in this cartoon, there's an input like RTL, constraints, libraries, tech files at the flow start at the top. And there's many steps and decision points like density screens or path groups or pin placements on the way to a complete outcome, which is your routed chip plus sign-offs, which is the flow end leaf. And your goal is to find the best possible end, but start to end is expensive. It takes weeks and millions of dollars of EDA licenses. We want the best possible end. There's a huge space of trajectories, and design has to live in this box of resources, servers, licenses, people, and weeks of schedule. So for as long as it has existed, EDA has been about high stakes, intractable optimizations at huge scale. Okay, this is our world. Takeaway: EDA equals optimization plus automation. Automation is where we look to AI, for example, and these are now the main levers for scaling. Next, AI and EDA, and since hindsight is easier, let me start with that. And ASP DAC, January 2018. I gave an invited talk on ML, EDA, and earlier that morning I gave this keynote talk. Note the slightly different titles, but they overlap. The keynote was largely really about ML for EDA. Machine learning gives scaling by modeling and prediction, by predicting tool outcomes and reducing wasted margins by correcting analysis errors, and by improving optimization, where modeling can give you a stack of optimization objectives that you could learn, and ultimately letting you get better outcomes from finite design resources. In the takeaways from the keynote, ML was foundation number one for what I was referring to back in those days as the last levers for scaling: quality, schedule, and cost, when sort of patterning and other things run out of steam. Then in the invited talk, this slide proposed ML EDA opportunities of modeling, prediction, correlation, automation to make design more efficient. There were technical challenges and industry challenges. The technical challenges included small and expensive data, the rapid changing of tool versions and technologies and designs themselves. This should sound familiar by now, right? And the industry challenges focused on who would drive ML into production design methodologies. Would EDA companies even allow their tools to be modeled and for models to be shared? Why would EDA companies welcome more effective use of design resources in the first place? And these questions indeed have become relevant over the past 6 years. And this slide also posed the challenge, can we measure to improve? Can we achieve big data in a collaborative or federated sense? Because even back then, we were hearing data is the new oil and such. Okay, so I'm almost done with this, blast from the past thing. Both of the talks had this slide near the end, a future ecosystem, and we can do this. So in this vision, the EDA vendors, the orange box, would open up their tool knobs. The researchers in the blue box would discover new deep learning models and loss functions for tools and designs. And IC designers, the red box, would supply domain knowledge and the training and validation data. At the end, EDA would sell better tools and private label AI models to the IC designers who would gladly pay for the benefits. And of course, as we know, this didn't happen. We didn't get the new tool knobs or the design data, and industry didn't really get the blue arrows. And I'm not sure what happened with this orange arrow in the bottom either. And so one conclusion about the past 6 years, because of these red X's, no access to tool knobs, no solution to the data problem, many of the to-do items from back then are still open. Okay. What actually happened was, however, we saw successes, and notably black box hyperparameter optimization in Cerebrus and DSO.ai or NVIDIA's AutoDMP. These are raging successes, I would say. People are very happy with the results. ML can give designers some useful hints, that's clear. It can help speed up physics analyses. There's also been a lot of excitement in the field and lots of papers have been written. Disappointments over the past 6 years. With the industry's consolidation into a small oligopoly, the tool silos are more closed than ever. It's harder to get data out or to use ML inference results to control the tool. Okay? It seems unlikely that we'll ever see companies sharing data or public foundation models. This is just reality. And the costs of machine learning have turned out to be significant. Not many ML methods have made it into production, as far as I know. Surprises. The rush to LLMs and generative AI. Much of the oxygen in the room, so to speak, has gone there now, and several use cases are clear. And I've been personally surprised by how much sway the EDA suppliers have gained over their customers, especially as they close up silos and interfaces. So one message today is that we as a community of researchers will have to work if we want to change this last point. And last, in the time since 2018, we now see concrete challenges and limits of ML EDA, quality of results, data scalability, generalization, validation, and cost. Okay, so closed AI ML platforms, which means the providers and their tenants, mean that academic research must enable itself. And we need to have high value targets with strong baselines and validations. Let me now briefly turn to the concepts of innovation and disruption. So, I'm just trying to connect all the dots in that title, which I unfortunately gave to Ian without much thinking through of what this talk would be. So, innovation. We hear it a lot these days about it. One definition of innovation is the implementation of creative ideas in an economic setting. So it's not the same as creativity or invention alone. And innovation requires innovators, people. It also requires the right conditions. In the economic setting, some innovations are disruptive. And this is a very famous concept from Clayton Christensen, Harvard Business School. I was at a Cadence CTC conference once where he was the keynote speaker. It was quite enlightening. Opportunity for disruption comes with either of two entry points that are at the bottom left of this picture. In this picture, low-end markets where the customer's needs are exceeded. I don't need that 2 nanometer capable $1.5 million place and route tool after all. Or new markets whose needs are unserved, but I do need a 3D chiplet integration planning tool or a multi-physics compact model extractor to drive my layout optimization, and I can't find one. Those are the two drivers for entry in this picture. The trajectory of disruption is that initial attributes are not valued by existing customers. So my open road 24-hour no human in the loop, which DARPA wanted, is not something that Qualcomm ever cares or cared about, never will. And so the disruptor is ignored. And then the attributes that existing customers do value, like PPA quality, steadily and sometimes rapidly improve. And one can always, if you're an innovator, take some motivation from this quote. And we're talking about co-pilots or open source or other things. Okay, paths forward. What will seed faster and potentially disruptive innovation? And here I feel like I must sound like a broken record for those of you who come to more than one of my talks every couple of years. The first item just has to be shared infrastructure for learning. And I don't care whether you mean education learning or machine learning, shared infrastructure is really important. What should I contribute? What do we call it? Who is the senior author? Does making a PR help me get a grant? Or I hope we can get over this kind of culture and reward system issue, because if we don't, we will stay together in some strange land of being toys and ankle biters. I feel this is the dark future of academia as the real world races ahead. So sharing is important. And some of you might know that the Design Automation Conference was originally the Design Automation Workshop. It started 60 years plus 1 day ago in Atlantic City, and it was originally called the Share Design Automation Workshop. I find it very poignant to see the MagTape drive and the punch cards in these logos for the first and fifth DA workshops, because I was born 8 months before the first DA workshop. And SHARE stood for the Society to Help Avoid Redundant Effort, which in my opinion is quite good to remember. Okay, so ML for EDA, including generative AI in many forms, amazingly has no infrastructure for research. Credit for this slide goes to Vidya. I see her sitting at that table back there. And it's been quite gratifying to see how open source EDA can provide this new playground for EDA researchers with 3 key pieces of infrastructure. And the first is Python APIs, many of which were written by Vidya and her student Bingyu. In this case, in OpenRoad, they wrap the underlying C++ APIs of the engines, and that gives you faster data generation than you can normally get using available TCL interfaces from established tools. Second is the ML-ready data formats. And I see Mark Wren here as well. Thank you to NVIDIA's open source CircuitOps, which leverages OpenRoad to model chip data as labeled property graphs, pandas data frames to store graph properties as features. And this streamlines the integration of ML algorithms into the EDA infrastructure. The third piece of the puzzle is additional Python APIs, this again implemented in OpenRoad, which enable results of ML inference to be integrated back into the database. So you have this feedback path from ML algorithms back into the EDA platform. So this is the kind of innovation that unblocks, so to speak, innovation in ML-based design methods. As I mentioned, Vidya and her student, with help from Rongjian and others at NVIDIA, gave this very nice tutorial at ASP DAC, and a paper just appeared at VTS in April. Okay. Then there's a question of where's the ImageNet or Hugging Face or Llama 2 that accelerates machine learning in EDA and IC design? If you don't know why this is currently impossible, well, I'll mention it in a few minutes, but you can probably guess. In March of last year, there was this US National Science Foundation workshop on shared infrastructure for machine learning EDA. Thanks to NSF for sponsoring this, and Sachin and Jiang Hu and others for organizing it. The link at the bottom has the workshop report and materials. By the way, all of this gets posted on my website, and there's a QR code at the end as well. This slide is from Professor Jiang Hu, who co-organized the workshop. And the left side draws parallels from our IC design and EDA world to the AI ML ecosystem's open infrastructure, the pre-trained models, the shared data sets, the contests, the libraries, the cloud scaling, the foundation models, and so on. So this infrastructure is notionally named SLICE. It's a proposed framework that envisions a similar basis for moving forward in ML EDA. And the hope is that this kind of infrastructure will lead to our taking advantage of the AI flywheel, which spins faster and faster on the exhaustive data. You may have heard Ruchir Puri talk about this. In this flywheel, which is here, more users create more data. More data leads to better models. Better models lead to better tools and chips that bring more value and profits, and better chips from ML EDA bring more users because managers like this sort of thing. Okay, so this is the dream. So the takeaway here is, we do research as researchers. We struggle. We do it to make a contribution. We're not leave no trace kinds of people, I feel. But to go beyond ankle biter or toy status, to make impacts at the leading edge, this will require shared, sustained, and very patient efforts. Enabling our grad students and research staff to think and innovate at longer time horizons, I feel, is very key. So for example, we all have CHIPS Acts in our home countries. Maybe we should be investing CHIPS Act money in some high ROI, long-term initiatives, not just what I see is stuff before the next election happens. So this is another thing as an action item for our world. And in that flywheel of AI that runs on the exhaustive data, where will the data come from? So there are very rational business reasons why, especially in our very consolidated industry, the activity of chip design has IP, usage, publication, work product restrictions imposed by many entities. Entities and people alike decide to be proprietary or open or whatever based on their respective value systems, and that's fine. But today, can we publish proprietary PDK or tool report formats? Of course not. Does modeling Innovus's clock tree synthesis constitute reverse engineering? Well, you know, I got a best paper for that in 2002 at ISQED, but today I don't know. And I'm not really interested in finding out what the attorneys think of it. And there's export control licenses, I mean, clauses in license agreements and lots of other stuff. So at ICCAD 2022, somehow my animation is messed up, I'm sorry. This picture pointed out that near free and free could be quite different from an access and usage standpoint, especially if we're talking about EDA research or enabling machine learning that will ultimately serve semiconductor-based system innovation. So can't share, can't model, can't share my model, can't integrate, can't post my students' projects or their lab solutions. These are all barriers. And I want to be quite clear here, what's going on. This picture pointed out that if you need a FlexML license server, if every student has to sign an NDA with a tool vendor, as is the case today, if the tool's documentation and TICL command names and reports and log files and outputs are all proprietary, which they are, which means no benchmarking, no uploading into ChatGPT, no commercialization of students' chip designs, then these are barriers. It's business, these are tools with fantastic technology embedded in them. But as a research community, my point is, if we want to work in relevant ways, we as a community need to build proxies. Pretty long-winded introduction here, but okay. You know that Skywater, IHP, Global Foundries have open sourced manufacturable PDKs. So kudos to all of these companies. But these aren't exactly TSMC N3E, which is where EDA and IC design researchers or startups want to play. So the question here is, can we make the design and research relevant characteristics of a source technology match the characteristics of a target technology? In this example shown in this plot, source is the open academic PDK called ASAP7, thanks to ARM and ASU in 2016 for doing this. And target is a closed commercial 7-nanometer foundry technology. The plot shows power versus effective clock period, the hockey stick, so clock period on the X, total power on the Y, for the JPEG design at 9 target clock periods. And the foundry 7-nanometer enablement hockey stick is in gray, and the auto-tuned ASAP7 enablement hockey stick is in orange, where both back end of the line RC constants and cell level scaling parameters like delay or slew or leakage are used in the tuning. So the auto tuning averages 2.3% loss, mean absolute percentage error of power and Fmax across the 9 target clock periods. This table shows auto-tune setting of scaling factors, where plus means scaling up of the nominal values, minus means scaling down by some percentage or ratio. And all of this code and scripts are open sourced in the IEEE, I won't say CEDA, I'll say IEEE Council on EDA's Design Automation Technical Committee's GitHub. So kudos to IEEE CEDA. And what if the enablement is unshareable? Or if there's no enablement? Because we need enablement as well. Here is Probe 3.0, which is an area of collaboration with my colleague C.K. Cheng, his great students. In a nutshell, Probe 3.0 is a framework for DTCO that automatically synthesizes cell library, GDS, and LEF using a satisfiability modulo theories solver, plus all of the design enablement needed to run commercial SPNR. And so the liberty and the RC parameters can also be auto-tuned, as in the previous slide, to match targets. Again, the scripts are open sourced in the DATC's GitHub and at UCSD. And here, many thanks are due to Cadence and Synopsys, to David Junkin, Angela Huang, Patrick Haspel, and others for defining the frameworks by which students could share their work in public. And so you should see the headers on the tickle scripts that are posted in the GitHub. That's the framework for sharing publicly. And what about designs? ETH Zurich and Berkeley and others contribute a lot in the RISC-V world, but inevitably we will need artificial designs to drive optimization and AI modeling with enough diversity and scale and volume. So I'm fond of saying that back in 2017, I thought this would be all crowdsourced. And I was telling people, you remember SETI at home, searching for extraterrestrial intelligence with your screensavers, or cure cancer at home? I still have hopes that we will crowdsource this. And here the interesting metaphor is mini brains. The pharma folks use blobs of neurons to gauge potential responses of real brains in drug discovery. And so imagine if you could make a netlist that behaves like a Cortex A72, but it's artificial, open, and 10 times smaller. So your flow will run 15 to 20 times faster. Can this mini brain A72 let you predict PPA for the big brain A72? Or, will it let you find the best flow knobs for the big brain? So imagine if your auto-tuning or your DSO.ai could magically run 15 to 20 times faster and find the same result. One value proposition for mini brains is in DTCO. Match the PPA Pareto of the big brain, full-scale design, but with less runtime needed in your explorations. And here, the research challenge is there. There's this tangle of size reduction and netlist generation, the loss function in the auto-tuning of your generators, and understanding the real-world bars for validation, acceptance, and impact. The left plot here is again a PPA hockey stick with clock periods on the x-axis, and this time with power per area on the y-axis. Red is artificial, blue is a 10 times bigger target design. They're pretty close. The right plot shows that the PNR runtime is reduced by 15 to 20x with the smaller artificial design. So these mini brains create a continuum for STCO with ring oscillators and critical path proxies on one end, and doing STCO traditionally with big CPU blocks and lots of resources on the other end. Mini brains are in between. A second value proposition is to match the Pareto of the big brain, the real full-scale design, across flow variants. And that's the whole point of DSO.ai or Cerebras. And I apologize if I'm giving short shrift to the value proposition. It's there. I just gave this shorthand description of what goes on in those offerings. But the point here is, in other words, can mini brains let us run Cerebras or DSO.ai style auto-tuning of flows 15 to 20 times faster? On the left is a PNR flow knob exploration with the mini brain with the Pareto front of the tuned flow parameters in orange, or the tunable flow parameters. So a bunch of tuples, right? On the right, we see that these two best flows are still quite good for the big brain real designs. This is a glimmer of hope, at least. Okay, and then there's proxy tools. These are, I shouldn't say proxy because these are real tools. They can tape out. So what I mean here is that these are tools that permit free usage, modification, benchmarking, uploading reports into ChatGPT, and all that. Basically open source EDA. And from the perspective of research and the scientific method, proxy tools complete the picture of having the freedom to enable others. You've heard me talk about this many times, of course. With proxy tools, we get clarity and transparency, while today's commercial offerings forbid benchmarking. We would get better science. Every result becomes reproducible and reusable. No more controversies about claims that can't be verified. And we would stop reinventing wheels. So grad students, thank you for open source. There's this amazing recent progress of open source EDA tools and infrastructure that, I mean, being an old person, I'm just so excited to see. I guess that's what happens when you get old. You get excited by stuff like this. IEEA and IPD, Verilator, Yosis, these are really inspiring efforts. IEDA and IPD, if you haven't heard about them, they're from China. They were presented by Professor Bei Yu at ASP DAC in January. And we should note this sentiment, open source is not a goal, but a way. And to strengthen this point, the program announcement on EDA for chiplets from China's national NSF calls for open sourcing of results in 8 of its topics. So, open source is happening around the world. More of the zeitgeist, the EU open letter, very famous, 500 researchers and educators as signatories. And as a side note, of course, I have to say this, the 5th Birds of a Feather meeting on open source EDA at DAC is tonight at 6:30 p.m. in room 3001. So if you're available, please consider joining for updates and discussions and to meet Birds of a Feather. If you can't attend, there's a Google form to register your interests and join in the follow-up discussion. Takeaway, proxy PDKs, enablements, designs, and tools. We need all of them. There's many gaps, and we will need coordination to close those gaps. Why? Because ML needs data, which depends on these proxies. And here are just a few top of mind calls to action, like written an hour ago into this slide. But I would call out the stackable multi-physics compact models where ML can really shine, and we need that million-x speed up. So packed folks, you have another 1000x to go. Finally, we need to come back home to home base. EDA is not just intelligent automation, but optimization as well. So optimization means get the best possible results within your limited resources. I said that already. And this is my favorite cartoon of the hockey stick Pareto frontier of clock period on the x-axis. Right is larger and slower. Left is faster and smaller. Area or power is on the y-axis, so up is larger and worse, down is smaller and better. We definitely want to push down and to the left. And I show open source or proxy EDA in blue and commercial EDA in red. It's dominating, of course. But what I claim for many years is that the sad part of this picture is not the blue-red relationship, which is inevitable. It's that we have no clue where optimal is. You can say that the location of optimal is protected by theoretical computer science because many EDA optimizations are NP hard. That was a joke, sorry. But actually the really sad fact is that even if I knew where the red curve was, I couldn't tell you because of license restrictions. What we do know is that open source EDA can access or has a number of elements that will help us get ever closer to optimality. Cloud, machine learning, GPU, benchmarking, transparency, innovation. Right? This freedom to benchmark and share data alone lets us move fast if we so choose. And that's again a choice. And I want to riff one more slide. I kind of like this slide because it talks about the law of optimization. The law is faster, better, and cheaper. You only get 2. Pick any 2. But I'm wondering with all these open source open proxies. Can we get all three at once? Especially when you throw in AI and machine learning and cloud and GPU. Apart from the benefits of benchmarking or open data for shared ML modeling and so on, we can see that open source is cheaper. It's no license costs, the community helps maintain it. You can do a lot of sampling and auto-tuning of all the ways you can set the flow and tool knobs. This alone gives you better solution quality. I am confident. The 1,024 chickens may beat the 2 strong oxen someday, not too far into the future. And then AI, ML, algorithms, and heavy end case optimizers like ILP or SAT solvers become affordable when your flow runs faster and farther. So QOR becomes better even as you decrease the number of attempts needed to find good solutions. And then you can run as fast as you want because you're not damaging your tool licensing model, for example. Clustering reduces problem size. Those mini brains I mentioned can help. GPU, cloud, they all give speedups. And then NRE decreases or you get more design iterations and quality within the same schedule. So this is another dream. This slide shows a commercial synthesis tool, and it's noise or chaos for the AES design in GF12 with a triple VT cell library. So the baseline target period in this picture is 280 picoseconds, and we step it by 0.01 picoseconds. That's 1/100th of a picosecond for 100 steps to the left and 100 steps to the right. So in these plots, you are seeing the results of 201 synthesis runs that vary only in the clock period constraints. And all of these runs sit within a 2 picosecond interval. But as you see, if you're up close, there's a 3% variation, 3.4% variation in the effective clock period, 38% variation in leakage power, 11% in standard cell area, 11% in total power. That's like an entire node of chaotic variation. If you can afford to make a lot of runs, that helps to denoise this. And this slide shows place and route tool noise for the AES design, same enablement. The 5 input netlists in this picture are synthesized with target clock periods ranging from 278 to 282 picoseconds, stepping by 1 picosecond per netlist. And then to study noise in place and route, we set the target clock period to 280 picoseconds. And then there's 5 times 201. So there's 1,005 PNR results in each of these plots. And we observe a variation of 15% in effective clock period across these 1,005 results. This is just huge, and this is why we do a lot of sampling and we pay a lot of money for auto tuners and so on. It's inevitable. We can't avoid this. So that's where open source can help. Number 2 example for optimization, this classic high-value target of enabling faster and more accurate exploration of architecture and SoC floor plan options. Shortening the time to useful PPA feedback is incredibly valuable. So this macro placer hierarchical RTLMP, which is /MPL2 in OpenRoad, understands RTL hierarchy and data flow. Some great professional engineers helped Jiang Wang and Ravi develop it. It delivers very human expert-like results. And this is an AI accelerator in GF12 LP with 760 macros. And for this test case, hierarchical RTLMP actually gives a pretty good result when you evaluate apples to apples by completing place and route with the Cadence Innovus 21.1 tool. So this macro placer is free, the quality is excellent, and these are final outcomes of a hybrid open plus closed source flow. And here's a recent work that makes early design exploration and assessment faster. It's example number 3 of optimization. DG Replace is a data flow aware GPU accelerated version of OpenRoad's current placement engine, which is called Replace. And this slide shows results in GF12 ARM enablement for a quad-core RISC-V called Black Parrot from UW. The new placer is compared against Replace and against DreamPlace 4.0, which is the previous state-of-the-art GPU-accelerated global placer. Maybe Evo will say it's the current state-of-the-art, who knows? The figures at the top show the post-routing results, and you can clearly see the data flow reflected in the DG Replace result, which is at the right. And the table shows post-route opt metrics, again from Innovus 21.1, again a hybrid open to closed tool flow. So all the metrics other than runtime are normalized to protect Foundry and IP providers' intellectual property, and WNS and TNS are normalized to clock period. But the bottom line is that the new placer dominates the other two placers. It places the more than 800K instances in 32 seconds. And so you would ask, can architects or RTL engineers use this kind of thing? And faster runtimes mean that we can afford auto-tuning, which is the black box hyperparameter optimization used in AI-boosted EDA. OpenRoad has had its own auto-tuner for several years now, but this slide shows auto-tuning of DG Replace using NVIDIA's open-sourced AutoDMP auto-tuner, still using the Black Parrot quad-core test case. And so the point is to show that you can leverage NVIDIA, OpenRoad, UCSD, and kind of blend them all together to get something better. And here we can specify hyperparameters and sampling ranges in a JSON file. AutoDMP uses a form of multi-objective Bayesian optimization, tree parson estimation, to generate candidate placements. We use OpenRoad Router's resource estimator and congestion mapper to assess the placements during this step 2. Run the Innovus PNR flow on the best 5 candidates. The best PPA is achieved by run ID number 14 out of 29, I think. And here we show the layout. And there's a code and a demo at the link in the QR code. But you can see this is much better even than the result I showed on the previous slide. The default is 0.90, et cetera, and the timing, all metrics get better. Finally, optimization strategies can do more in a given unit of time because there's multiprocessing and the cloud if you're not limited by the number of copies of runs that you can launch. So here's what my students and I call tomography. In this case, run the early global router a bunch of times on a placement to get a very rich set of images. Each run takes less than a second, and you can do them all in parallel. 1 second. Then set up your expensive detailed routing run with a learned model or an inferred set of routing blockages based on this rich information. I call this ML magic. It's at interstices, and there's a lot of opportunities. In this case, the handoff from place to route. How can I condition the problem better for success with ML? And this is too busy, but this slide, if you download it later, shows how a human would make sure that routing succeeds, given a placement. The human would run the router, look at the result, handcraft routing blockages based on the violation markers, and iterate. So running the detailed router for an hour and a half, multiple times over and over. But in tomography, using the richness of features from tomography, one model can predict blockage region shapes. A second model can select which combination of blockages to apply. And the ML approach doesn't have to keep running the detailed router. It achieves a fairly substantial DRC reduction compared to the default of no blockages. It beats the human baseline by about 20% as well. For a Cortex A53 in GF12, tomography basically produces better routed wire length and power, as you might expect, because it avoids congestion. So these are just a few examples of the richness, the sampling, the hybrid flows, the GPU acceleration, doing more in unit time, that are all still available just in basic CAD optimization. And if you look at how fast we can run with an open papers with code, GitHub culture, the yellow items are coming online as we speak. This is showing how hierarchical RTLMP that I showed is, or, DG Replace is built on Replace, Dreamplace is built on Replace, Auto DMP is built on Dreamplace. And I showed results of wrapping Auto DMP and its Bayesian optimization around DG Replace. All this is happening within 18 months. And similarly, in the partitioning and floor planning universe, from open source SpecPart in 2022 and RTLMP in 2022, so many results have quickly appeared. But if you look down at the bottom, you'll see HMetis. There was a quarter century of stasis in this field after HMetis, which was not available to researchers in source code form. So optimization, just basic stuff, has rich vistas yet to be explored. Openness allows us to all race forward faster. And so the call to action here is we should all go out and do this. 48 minutes and 32 seconds. So these are a few of the takeaways that have been accumulated so far. There are really a ton of others. I'm happy to chat about them anytime, maybe at the Birds of a Feather meeting tonight or at another time. And thank you very much for the invitation and for your attention.